Hello and welcome to N38, continuation of our discussion with acids and bases. This time we are focusing specifically on weak acids and bases. So, jump right into it. We all know that weak acids and bases, when they react, they form an equilibrium. So, best way to look at it is just to attack it from a problem perspective and go through the steps in solving for the pH. Quick reminder, when it comes to strong acids and bases, we know that the concentration of the strong acid or base is equal to the concentration of the ions. Therefore, take the negative log and have a good day. But when it comes to weak acid and bases, because it's not 100% dissociation, we have to attack it from an equilibrium standpoint. So, step one, we gotta write the dissociation equation. Okay, easy enough. It's an acid, so we know that it will ionize into hydrogen and acetate. Now, you could include water as a reactant, but notice that your hydrogen ion would then be written as hydronium. That is the only difference, but when it comes to acids specifically, you do not need to include water. Step number two, we do ice tables. So we all should remember ice tables from equilibrium. They're the same thing, nothing's changed. So again, we know the initial concentration of my acetic acid, and we have no ions yet before anything dissociates. Well, obviously I can only go in the forward direction, so my change, minus x, and plus x, reminder, any coefficients in your equation act as multipliers in this row. Well, put it together from an equilibrium perspective, and we get our equilibrium line. All right, step three, set up the law of mass action. You guys have done this many of times. Products over reactants raised to their stoichiometric coefficients. So if I do that and then plug in the information, I'll get something that looks like this, where the equilibrium constant, Ka, in terms of acid, equal to products over reactants, raise their coefficients. However, we'll see that we'll see that the minus x has disappeared. Well, welcome to the 5% rule. 5% rule has you compare the Ka or Kb, whatever type of reaction you're dealing with, compare that to the initial concentration. If the equilibrium constant is 1,000 times smaller or more than the initial concentration, then I can assume the 5% rule, meaning that the x value in 0.5 minus x is less than 5%. It's very, very small, so the initial concentration is not really changing at all. Any questions on the 5% rule? Okay. So I solve for x, which also represents the hydrogen concentration. And I get this number for this problem. No quadratic equation needed. Makes life a heck of a lot more simple. But now I have my hydrogen concentration. Now I can convert hydrogen concentration to pH. Nothing new there. You've done this before. Any questions? Alrighty then. Moving on. Looking at weak bases with water. So a base reacts with water, producing its conjugate acid and hydroxide ion. So we'll take this reaction as an example. Our conjugate acid and our hydroxide ion are produced. When you write the reaction of a weak base, you have to, required, to include water. When you write a reaction with a weak acid, you do not have to use water. Again, with weak bases, you must include water. Again, it's an equilibrium. It's a weak base. So I can write my law of mass action how I've always done. Everything's going to be aqueous. Notice water's not in there because it is a liquid. Questions on this? Okay. So a couple KBs just to get an idea. Again, don't need to memorize these because you're going to be given all constants that are needed. So don't need to worry about that one. All right, so the generic reaction, as we kind of saw for weak acids, but here for weak bases, is again a base plus water gives me my conjugate acid and hydroxide, what we just saw. And again, law of mass action, nothing new here. Yes, all weak bases do this. Do not endeavor to make this complicated. It's really this simple. Questions on this? Okay. All right, when it comes to doing a weak base equilibrium problem, everything we just did for a weak acid is identical for a weak base problem. They are the same in every possible way except one. If you notice, hydroxide is produced in the reaction. So here's my equation. We get hydroxide. So by solving and performing the same steps of a weak acid for this problem, the concentration, or my X value that I solve for, will represent hydroxide ion. Hopefully you can see what's the one difference we have to do. So ice table, again, nothing new. See, I'm even using the exact same numbers. Literally, because you can see the Kb for ammonia at the top is actually the same as the Ka for acetic acid previously. So literally, it's identical in this example. So law of mass action, plug it in. See, nothing new here. Yes, I am going faster because you've already written this down. Now step 4, solve for X. But again, notice X represents hydroxide, not hydrogen, when you deal with a weak base. Plug it in. Oh, hey, look, it's the same number. Now, here's where things start changing. We got to convert to pH, just like before. However, we have the POH, but now we have to end up getting to the pH. So everything you've seen with weak acids and weak bases is identical, except this last step. You have to do 14 minus the POH to get to your pH. Any questions on weak bases? Okay. Thank you much. Until next time.